I want you to picture a railway track.
Yeah.
Just a standard, single set of iron rails stretching out to the horizon.
Okay.
You're on the train. The engine is roaring, the wheels are clacking, and you are just moving relentlessly forward. You look out the back window, and you see the station you just left. That's the past.
Right, it's getting smaller and smaller.
Fading into the distance. And you look forward, and there's the next station. The future.
It's a very comfortable image. It's orderly. It makes sense.
It is orderly. But here's the rule of this specific railway.
Yeah.
The train has no reverse gear. You can never go back to the station you just left. You can't stop, and you definitely can't turn around. You're locked into this one-way trip until the line ends.
And that's how we all intuitively understand time, isn't it? It's an arrow. It flows one way.
Exactly. Yesterday's gone, tomorrow hasn't happened, and we are sort of stuck in the now.
That is the classical Newtonian view. Time flies straight and true, and once it's loosed from the bow, there's no calling it back. It's intuitive, it feels right, and for most of human history, that was the only way to think about reality.
But today, on this deep dive, we are going to see if we can derail that train. We're going to look at whether that straight track might actually have loops or switchbacks or maybe hidden tunnels that connect the end of the line back to the beginning. We're asking the big one today, is time travel actually possible?
And we aren't talking about magic or, souped-up DeLorean cars, at least not primarily. We are talking about the hard physics of general relativity and quantum mechanics.
So this is real science.
This is where we move from the realm of completely impossible to the much more interesting realm of highly improbable but mathematically allowed.
That is a very specific distinction. Mathematically allowed sounds like a loophole a lawyer would find in a contract.
In a way, it is. We're going to look for the loopholes in the laws of physics. That's the mission.
Okay, so the mission today is to build a time machine, or at least to see if the blueprints even exist. We're going to look at rotating universes, cosmic strings, shortcuts through space, and probably the weirdest concept I've ever heard of, negative energy.
Which all leads us to the ultimate question. If the blueprints exist, why hasn't anyone built one? Or, more pointedly, if they will build one in the future, where are all the tourists?
Right. Why aren't we seeing people from the year 3000 walking around taking selfies with, I don't know, a gladiator?
It's the Fermi paradox, but for time travel. A profound silence.
But before we get to the tourists, let's start with the history. Because I always thought time travel was purely the domain of H.G. Wells and science fiction writers. I didn't think serious scientists gave it the time of day.
For a long time, they didn't. It was considered a fringe topic, something that would, ruin your career if you focused on it too much. But that all changed with a man named Kurt Gödel.
Gödel. The name is definitely familiar. He's the math guy, right? The incompleteness theorem.
That's him. He basically shook the foundations of mathematics by proving that there are true statements that you just cannot prove.
Right.
A brilliant, albeit somewhat eccentric mind.
Okay, so what does a mathematician have to do with time travel?
Well, the reason he matters for us today is because of who his best friend was.
Let me guess. Albert Einstein.
The one and only. And you have to picture this. It's 1949. We're in Princeton, New Jersey, at the Institute for Advanced Study. This is where the smartest minds in the world gathered. And every day, you'd see these two figures walking home together. Einstein, with the iconic crazy hair, and Gödel, who was very slight, very serious, usually in a heavy coat. They were inseparable.
I love that image, the physicist and the logician just walking and talking. What were they even talking about?
The nature of reality, mostly. Einstein had published general relativity decades earlier, which, fundamentally says that gravity is the bending of space and time. Mass tells space how to curve. Space tells mass how to move.
Right, the old bowling ball on the trampoline visual. It curves the fabric of space.
Precisely. Now, Einstein thought he understood the implications of his own theory. He believed that while space could warp, time was still fairly well behaved. It marched forward. But Gödel, being Gödel, decided to take Einstein's equations and push them to their absolute breaking point.
He was stress testing his friend's life's work.
Exactly. He wanted to see if he could find a solution to those equations that Einstein himself had missed. And he did. He found something. He presented a model of a universe, a mathematically valid, perfectly legal solution to general relativity, where the entire universe is rotating.
Rotating. You mean like a planet rotates, the whole universe spinning?
Yes, the entire fabric of space-time swirling around like water going down a drain. Now, in this rotating universe, the combination of gravity and the centrifugal forces do something very, very strange to light and to time. They drag them.
Drag them out?
They drag the light cones, which basically define the path of light and the boundary of cause and effect, into a tilt. If the rotation is fast enough, the path of time itself, it curves into a circle.
So in a Gödel universe, time isn't a straight line. It's a loop.
It's what physicists call a closed time-like curve. That's the technical term for a time machine. It means if you got in a rocket ship and traveled far enough along this curve, you wouldn't just go far away in space. You would eventually arrive back at your starting point in both space and time.
Wait, let me make sure I'm getting this right. I get in my rocket, I blast off. I fly for, say, 10 years ship time. I turn around and come back. But because the entire universe is spinning and dragging time with it, when I land, it's not 10 years later. It's yesterday.
It could be 10 years before you left. You could theoretically get out of your rocket and shake hands with yourself before you even packed your bags for the trip.
That breaks my brain. How did Einstein react to this? I assume he was impressed that his friend solved the math.
Oh, he was impressed, but also deeply disturbed. The records show he was upset by it. Einstein was a determinist. He liked a clear cause and effect. A causes B. If B can come back and prevent A from ever happening, the whole structure of causality falls apart.
It's a ghost in the machine he built.
It was. He felt this possibility of time travel was a flaw in the theory. He hoped it was just a mathematical oddity, not a physical reality.
So here's the billion-dollar question. Do we live in a Gödel universe? Is our universe spinning?
That's the catch. We have checked. We've looked deep into space, at the distant galaxies, at the cosmic microwave background radiation, the echo of the Big Bang, and as far as we can tell, the universe is expanding, but it is not rotating.
Okay, so Gödel found a loophole, but it's a loophole for a different universe. It doesn't apply to us. Bummer.
It doesn't apply to our specific geometry, no. We don't have that global rotation to drag us back into the past.
So that's one blueprint scrapped. But you mentioned something else in this natural phenomena category, cosmic strings.
Ah, yes, cosmic strings. These are, if you can believe it, even stranger than a rotating universe.
The name sounds deceptively harmless. String makes me think of yarn.
Think less yarn and more a crack in the fabric of reality itself. Cosmic strings are these hypothetical defects in spacetime. Imagine you have a frozen lake. The ice is mostly smooth, but sometimes you get these jagged cracks where the water froze unevenly.
Okay.
Cosmic strings are like those cracks, but formed in the instant after the Big Bang when the fundamental forces of the universe were crystallizing.
So they are leftovers from the creation event. What do they look like?
Well, they would be incredibly long, maybe stretching across the entire observable universe, but thinner than a proton. The real kicker, though, is their density. It's unimaginable.
Give me a comparison, something I can wrap my head around.
A single inch of cosmic string would weigh something like 1,000,000 billion tons. The tension on these things is astronomical. For example, if you attached one to the Earth, the string's tension alone would accelerate our entire planet from 0 to 60 miles per hour in about a 30th of a second.
That's a lot of tension. So how does this lead to time travel?
Because they are so thin and so heavy, they create this incredibly intense and weirdly shaped gravitational field around them. It's not like a sphere around a star, it's more like a wedge. Space-time's missing a slice around a cosmic string.
Missing a slice.
Yeah. And the math suggests that if you have two of these strings flying past each other at incredibly high speeds, or maybe one string snapping past a black hole, the space-time around them gets so warped, so twisted up, that again, we get those closed time-like curves.
It warps space so hard, it literally bends time into a loop.
Exactly. You could fly a ship in a sort of figure-8 pattern around these two moving strings and arrive back before you left.
But I'm guessing, since I haven't heard about a cosmic string tourism board, that we don't have any of these nearby.
We haven't found any. We've looked for the gravitational lensing they would cause, how they would bend light from distant stars in a very specific double image pattern, but so far, nothing. And similar to the rotating universe, the evidence from the Big Bang suggests our universe was born remarkably smooth. It wasn't distorted enough to create these strings in abundance.
So nature is 0 for 2. The universe didn't just gift us a time machine on a silver platter.
It appears not, which is probably for the best, really.
Which means if we want to loop the track, we have to do it ourselves. We have to engineer it. And usually when we talk about space travel, the first thing we think of is speed. We want to go fast.
Speed is the natural place to start. And this brings us to the second major path to traveling in time, breaking the speed limit.
The speed of a light.
The universal speed limit, about 186,000 miles per second. Now, we know from special relativity that time is not constant for everyone. This is the famous twin paradox.
Wait, let's recap that quickly. I have an identical twin brother. I stay on Earth. Maybe I take up gardening. He gets in a super fast rocket and flies at 99% the speed of light to a distant star and comes back.
For him, on the ship, maybe only a few years pass. But because he's moving so fast, his time is running slower relative to yours. When he returns, you might be an old man with grandkids, and he has barely aged a day. He has effectively traveled into your future.
But that's a one-way ticket.
Correct. That is time dilation. It allows you to skip forward. You can go see the year 3000, but you can't come back to 2024 to tell us about it. It's useful for astronauts who want to see the galaxy in a single lifetime, but it's kind of heartbreaking because everyone they know will be long gone when they return.
So, to go back, we need to do something much more radical. We need faster than light travel. FTL.
FTL. It's the staple of Star Trek, Star Wars, Battlestar Galactica. They push a button, the stars streak by, and they're across the galaxy in time for dinner. But in real physics, FTL and time travel are inextricably linked. If you can do one, you can do the other.
I've heard this before, but I've never truly understood why. Why does moving fast through space equate to moving backward in time? It feels unconnected.
It all comes down to one of the weirdest ideas in all of physics, the relativity of simultaneity.
Okay, this is the part that usually hurts my head. Walk me through it slowly.
Okay, let's use the example from the source material. It's a good one. It involves the Olympics.
I'm looking.
We have two events. Event A is the final of the 100-meter dash at the 2012 London Olympics.
Got it. Usain Bolt winning.
And Event B is the grand opening of the 100,004th meeting of the Galactic Congress on a planet orbiting Alpha Centauri.
A very specific event.
Okay. Now, in our frame of reference, standing still on Earth, let's say these two events happen at the exact same time. The starting gun fires in London at the exact instant the space gavel comes down on Alpha Centauri. They are simultaneous.
Okay, makes sense.
But simultaneous is not absolute. It depends on how you're moving. Imagine a spaceship flying from Earth towards Alpha Centauri at, say, half the speed of light.
Right.
From the perspective of the people on that spaceship, they are moving towards the light from the Congress and away from the light from the race. Because of this, their definition of now tilts. For them, the Galactic Congress opens before the race in London starts.
Just by moving, they change the order of events.
They change the perceived order. It doesn't break causality yet because they can't act on that information. The light from the race still reaches them after the light from the Congress.
This is weird, but it doesn't sound like time travel yet. It just sounds like they're seeing things in a different order.
It becomes time travel when you introduce FTL. Let's say our spaceship can travel faster than light. Now, the people on that ship see the Congress open on Alpha Centauri, then they hit their warp drive, and they fly back to Earth faster than light.
They beat the signal. They beat the light from the race.
They do more than that. Because of how space-time is structured, if you travel from Event B back to Event A faster than light, there are reference frames in which you arrive back on Earth before the race even started. You could get there in time to place a very confident bet on Usain Bolt.
Wow. Okay. So faster than light travel isn't just a way to get places quickly. It's a way to rewrite the timeline of who saw what when.
It fundamentally breaks the sequence of cause and effect for some observers. There's a famous limerick about this, isn't there?
Yes. There was a young lady of white who traveled much faster than light. She departed one day, in a relative way, and arrived on the previous night.
It's cute, but it's mathematically accurate. If you can break the light barrier, you break causality.
So why don't we just build a really, really fast engine? What's stopping us?
The energy barrier, it's a wall. According to special relativity, as an object with mass approaches the speed of light, its relativistic mass increases.
So my spaceship gets heavier.
In terms of the energy needed to push it, yes. To get a single grain of sand to 99.9% the speed of light takes a phenomenal amount of energy. To get it to 100%. To actually reach light speed, it would take infinite energy.
Infinite?
Not just all the energy in the sun, literally infinite energy. The laws of physics essentially put up a giant do not cross tape at light speed. You cannot accelerate your way through it. It's impossible.
Okay, so we can't find a time machine in nature from Gödel or cosmic strings, and we can't run fast enough to break the time barrier with FTL. This is feeling like a dead end.
It's a dead end for speed, but it's not a dead end for geometry. If you can't run fast enough to beat the light, maybe, you can take a shortcut.
A shortcut, like a tunnel.
Exactly. Imagine you want to get from one side of a mountain to the other. You can climb over the top, that's the long, slow way, or you can drill a tunnel straight through the base.
A tunnel through the universe.
Precisely. This is where we finally get to wormholes.
I feel like everyone knows the visual for this. You take a piece of paper, you draw 2 dots on it. Point A is Earth, point B is Alpha Centauri. The distance on the paper is, say, 10 inches.
Right. And in reality, it's 20 million miles, a very long way.
But if you fold the paper in half so the dots are touching and you punch a pencil through them, the distance becomes almost 0. You've connected them directly.
That is the perfect analogy. In general relativity, space-time is the paper. A wormhole is that pencil tunnel. It connects 2 points that are far apart in normal space with a very short throat.
So I could step into a wormhole on Earth and step out on Alpha Centauri, a few seconds later.
Theoretically, yes. And because you traveled that huge distance effectively instantly, without actually exceeding the speed of light locally in the tunnel, you have beaten the light beam that had to take the long way around.
And since we just established that beating the light beam allows for time travel.
You have a time machine. You can arrange the mouths of the wormhole, perhaps by moving one of them at high speeds for a while and bringing it back, so that stepping through it takes you not just to another place, but to another time, specifically to the past.
This sounds incredibly promising. Do we have actual blueprints for this?
We do. As I mentioned, Einstein and his student Nathan Rosen described this exact thing back in 1935. They called it an Einstein-Rosen bridge.
That sounds so much classier. I'm just taking the bridge back to the 1920s for a bit.
It does, but there was a catch. There's always a catch, isn't there?
Always.
Einstein and Rosen found that these bridges are inherently violently unstable.
Unstable how? Like a rickety rope bridge that might break.
Worse. Much worse. The moment you create one, gravity tries to slam it shut. The throat of the wormhole pinches off into a singularity, a point of infinite density, so fast that not even light can cross it. If you tried to fly a spaceship in, the tunnel would collapse and crush you out of existence before you got halfway through.
So it's a trap. It's a bridge that snaps the very moment you step on it.
A cosmic Venus flytrap. Unless you can prop it open.
How do you prop open a hole in space-time? You can't exactly use steel beams and 2x4s.
You need something that pushes against gravity. Normal matter, rocks, air, stars, you, me, all has mass. Mass creates gravity, which pulls things together. In the language of relativity, it creates positive curvature, like the surface of a sphere.
Okay, gravity pulls in.
To keep the wormhole open, you need the opposite. You need the space-time in the throat to curve outward, like a saddle shape. To do that, you need something that creates anti-gravity. You need exotic matter.
Exotic matter. Is that just a fancy scientific-sounding word for magic?
It's close. It refers to matter with negative energy density.
Negative energy. Okay, stop. I can understand negative temperature. I can understand being in negative debt. But negative energy. Energy is stuff. How can you have less than 0 stuff?
That is the big intuitive roadblock. In classical physics, Newtonian physics, you can't. Energy is always positive or 0. But in quantum mechanics, the rules are looser.
Are we going to the liberal bank of quantum mechanics now?
That's the perfect analogy. Think of it like a bank account. In the classical world, the bank manager says you can never be overdrawn. Your balance must always be 0 or higher.
Responsible banking. I like it.
Sure, but the quantum bank manager comes along and says, look, I don't really care if you're overdrawn in this specific checking account, as long as your savings account have enough money to cover it so that your total net worth is positive.
So I can have negative money in one pocket as long as I have extra positive money in the other pocket to balance it out.
Yes, the universe allows you to borrow energy from the vacuum of space, creating a localized region of negative energy, as long as you create a region of positive energy nearby to balance the books overall.
This still sounds like an accounting trick. Is it real? Is there any proof we can actually make negative energy?
We can, and we have. It's called the Casimir effect.
The Casimir effect. This is the experimental proof.
This is the smoking gun that negative energy is real. It's an experiment first proposed by the Dutch physicist Hendrik Casimir back in 1948, and it's deceptively simple in its setup. You take 2 metal plates, perfectly flat, perfectly polished.
Okay, 2 plates.
You put them in a perfect vacuum, what we would call empty space, and you bring them very, very close together, microns apart, closer than the width of a human hair.
And what happens?
They get pushed together.
By what? Gravity? Magnets?
No. They are uncharged, and the force is much stronger than gravity would be between them. They are pushed together by the nothingness of empty space itself.
How can nothing push something? That makes no sense.
Because nothing isn't nothing. This is one of the deepest truths of quantum theory. The vacuum of space is actually a seething, chaotic soup of virtual particles. They are popping in and out of existence constantly, in pairs. Photons, electrons, and positrons, flashing into existence for a fraction of a second and then annihilating each other. It's like a chaotic ocean of energy.
Okay, so empty space is an ocean of particles.
Think of those particles as waves on that ocean. Some are big rolling waves with long wavelengths. Some are tiny ripples with short wavelengths. Now imagine putting our two plates into that ocean, like the parallel walls of a harbor.
Right, the plates.
Outside the plates, out in the open ocean, waves of any size can exist. Big ones, small ones, everything in between. But between the plates, in that tiny narrow gap, only very specific small waves can fit. The big rolling waves with long wavelengths literally can't squeeze in there.
So there are fewer possible waves between the plates than there are outside.
Exactly. And because all these waves carry energy, there is more energy, more push from the crashing waves on the outside of the plates than there is from the tiny ripples on the inside.
So the outside ocean pushes the plates together.
Precisely. And this force has been measured. It's real. And in physics terms, if we define the energy density of the normal vacuum outside as 0, and there is measurably less energy inside,
The energy inside is negative.
it is a region of negative energy density. The Casimir effect proves that we can create negative energy in a lab. It's a tiny amount, but it's real.
So if we could scale that up, if we could build a Casimir machine the size of a planet, or engineer materials that do this on a massive scale,
We could, in theory, generate enough negative energy to prop open the throat of a wormhole. We could stop it from pinching off. We could stabilize the bridge and make it traversable.
Okay, so let's review the checklist for a time machine.
Let's do it.
1. Does general relativity allow for loops in time? Check. Gödel proved it. 2. Can we build a shortcut, a tunnel through space-time? Check. That's a wormhole. 3. Can we prop the door open so it doesn't kill us? Check. We can use negative energy, which we know exists thanks to the Casimir effect.
The blueprints look solid, don't they?
It sounds like we're ready to build this thing. I mean, what's stopping us?
Well, now we're leaving the engineering department and walking into the philosophy department, and they have some very serious complaints.
The paradoxes.
The paradoxes. The most famous one, of course, is the grandfather paradox.
I feel like everyone knows this one, but let's play it out because the implications are just terrifying. I build my beautiful, stable wormhole. I use it to go back to, say, 1920. I find my grandfather.
He's a young man, let's say, hasn't met your grandmother yet, no kids.
And because I'm a complete psychopath in this particular thought experiment, I shoot him.
Okay, dark. But follow the logic. If he dies in 1920, he never meets your grandmother. Your father is never born. And if your father isn't born, you are never born.
But if I'm never born, I can't build the wormhole. I can't go back to 1920. I can't shoot him.
So he lives. He's fine.
Which means he meets my grandmother. My father's is born. I am born. I build the wormhole. I go back.
And you're stuck. It's an infinite loop. It's a logical contradiction. And the universe really, really hates contradictions. It's like trying to divide by 0. The whole system just crashes.
So how do physicists resolve this? Or do they just sort of throw up their hands and ignore it?
There are two main schools of thought, two possible ways out. Solution A is called the consistent histories hypothesis.
Consistent histories. What does that imply?
It implies that the past is immutable. It's a fixed, solid block of space-time. You can go back and visit it, but you cannot change it. In fact, you are already part of that history. Your visit to the past has already happened.
So I go back to 1920, I find my grandfather, I aim the gun.
And the gun jams. Or you'd slip on a banana peel. Or a bird flies in front of the bullet at the last second. Or, in a really cruel twist of fate, you shoot him, but you only wound him, and the nurse who tends to his wound in the hospital is your future grandmother, and that's how they meet.
So my attempt to change the past actually causes the future I was trying to prevent.
It's the ultimate cosmic irony. But the point is, you cannot create a paradox. The laws of physics will conspire to prevent you from doing it.
But wait, that implies I don't have free will. If I'm in the past, I can't choose to pull the trigger successfully.
That is the profound and disturbing cost of the consistent histories solution. If you are in the past, you are an actor who has lost their script but is forced by the universe to say the lines and perform the actions anyway. You are a puppet of causality.
I hate that. I really, really hate that. Give me solution B. Please tell me there's a better option.
Solution B is the many worlds, or alternative histories hypothesis. This is the logic from Back to the Future Part 2.
Marty McFly creating the bad 1985.
Exactly. In this view, when you go back and successfully pull the trigger, you don't change your own past. Instead, the universe splits.
It branches off.
Yes. There is timeline A, the one you came from, where your grandfather lived and you were born. And now you have created and entered timeline B, a whole new universe where he dies and you will never be born in that timeline. You didn't change your past, you created a new separate future.
So I can never get back to the timeline I left. I'm stranded.
You're stranded in this new reality you've made. But at least in this version, you have free will.
That's a pretty heavy consequence either way.
Yeah.
Now, interestingly, the source material mentions the physicist Richard Feynman here. What was his take on all this?
Feynman had this beautiful idea called the sum over histories. He proposed that to get from point A to point B, a particle doesn't take just one path. It takes every possible path all at once. It goes around the sun, it zips off to Jupiter and back, all simultaneously.
A quantum free-for-all.
Right. But when you apply this idea to time travel, some physicists argue that Feynman's math actually supports the consistent histories view, the no free will version.
Really? Why?
Because the math generally assumes a single self-contained spacetime. It doesn't easily account for hopping between different universes. So if your time machine keeps you in this universe, the sum over histories will always average out to a single self-consistent history, a paradox-free one.
So we might just be stuck with the gun jams scenario.
It's a very strong possibility. But, there is a place where we know time travel happens. We don't have to speculate. It happens every day inside every atom in your body.
We're going microscopic now.
We are, to the weird world of quantum mechanics.
I remember hearing that antimatter is involved here somehow.
It is. Fundamentally, Paul Dirac, another one of the greats, discovered antimatter purely through mathematics before we ever found it in a lab. And when you look at the equations for, say, a positron, which is an anti-electron, it looks exactly like the equation for a normal electron, but one that's moving backwards in time.
Wait, is that just a mathematical trick? A cute way of writing the formula? Or is it literally moving backward in time?
In quantum field theory, there is no difference. They are one and the same. An antiparticle moving forward in time is physically indistinguishable from its corresponding particle moving backward in time.
Help me visualize this.
Okay, imagine you're watching a movie of a particle moving across your screen from left to right. Now just play the movie in reverse. The particle moves from right to left. That's all it is.
So when we see particle accelerators smashing things together and creating antimatter, we are, in a sense, watching tiny bits of time travel.
You can interpolate exactly that way. Take pair creation. In the vacuum, an electron and a positron can appear out of nowhere, move apart for a moment, and then come back together and annihilate, disappearing in a flash of light.
Poof, gone.
But you can draw that event as a single continuous line in space-time. An electron is moving forward in time. At some point, it gets hit by a high-energy photon, and it pulls a U-turn in the time dimension. It starts traveling backward in time, which we perceive as a positron. Then it gets hit again, pulls another U-turn, and moves forward in time again as an electron.
So annihilation isn't destruction. It's just the particle turning around in time.
It's like a single thread making a zigzag stitch in the fabric of time.
That is beautiful and also deeply confusing.
And it solves a problem with black holes, too. Stephen Hawking famously proved that black holes aren't actually black. They glow. They emit radiation.
Hawking radiation.
Exactly. But the whole point of a black hole is that nothing can escape its gravity, not even light. So how does radiation get out?
I always just assumed it. Leaked somehow.
The time travel explanation is much cooler. A virtual particle pair forms right at the event horizon. One falls in, the other escapes. But you can view the one falling in as an antiparticle traveling backward in time, coming out of the black hole from its future, and then turning into a normal particle moving forward in time, away from the hole.
So the radiation we see is actually stuff from the future of the black hole, traveling back to the present, just so it can escape.
In a sense, yes. Quantum mechanics not only allows time travel on this microscopic scale, it seems to rely on it to make the equations balance.
Okay, so subatomic particles do it all the time. The math for big stuff allows it. We have blueprints for wormholes and the fuel to keep them open. So I have to ask the question again, and it feels more urgent now. Why aren't we seeing tourists? If future humans can build these things, why aren't they here stopping wars or buying up Apple stock in 1980?
This is the big one, the Fermi paradox of time travel. If it's possible, where is everybody?
Maybe they're hiding. The temporal prime directive?
The source material is skeptical of that. Humans are notoriously terrible at keeping secrets. If thousands of people from the future could time travel, someone, somewhere, would have messed up and revealed themselves by now. A time cop agency seems unlikely to be a 100% effective forever.
So if they aren't here,
Yeah.
maybe they just can't get here.
This leads us to the final and perhaps most significant hurdle of all, the chronology protection conjecture.
That sounds like a law passed by the universe itself, the Paradox Prevention Act of the cosmos.
It was proposed by Stephen Hawking. He basically said, the laws of physics conspire to prevent time travel on a macroscopic scale, to keep history safe for historians.
How? How does the universe enforce this? Does it just say, no, you can't build that?
It uses physics. Specifically, it uses that quantum vacuum foam, and it creates a feedback loop from hell inside the time machine itself.
A feedback loop.
Okay.
Let's go back to our beautiful, stable wormhole. We've propped it open with negative energy. We've built the time machine. We're ready. We turn it on.
Okay, switch is flipped. The door of the past is open. The moment you connect the past and the future, you have created a loop. Now, remember those virtual particles? The ones popping in and out of the vacuum constantly?
The ocean foam?
Yes. Normally, they appear and disappear in a flash. But now, a virtual particle can appear, and instead of disappearing, it can enter the mouth of the wormhole, travel back in time, and exit a moment before it entered, where it can meet itself.
It overlaps with its past self.
And then it can go through the wormhole again, and again, and again.
It's caught in a loop.
Think about being on a stage with a microphone. If you put the microphone too close to the speaker it's hooked up to, what happens?
Oh, that awful screeching noise. The high-pitched squeal. Feedback.
Exactly. The sound goes into the mic, gets amplified, comes out the speaker, goes back into the mic, gets amplified more. It gets louder and louder in a fraction of a second until it blows out your eardrums.
Okay, I have that painful sound in my head now.
Now imagine that, but instead of sound, it's energy, it's radiation. A beam of radiation made of these virtual particles loops through the wormhole an infinite number of times in the very instant the machine is turned on.
So the energy density at the mouth of the wormhole spikes to infinity.
Instantly. A bolt of infinite radiation shoots through the throat of the wormhole.
And I'm guessing delicate negative energy structures and, human time travelers don't like being hit with bolts of infinite radiation.
No. It would almost certainly vaporize the machine, collapse the wormhole by creating a massive gravitational field, and kill anyone standing nearby. The universe essentially booby-traps the door. The moment you unlock it, it explodes in your face.
That is the chronology protection conjecture. The feedback destroys the bridge before you can cross it.
That is the argument. It's the universe's immune system fighting off the infection of paradoxes before they can start.
Has this been proven? Is it a law?
No, not at all. It's a conjecture. A very educated guess. We would need a full theory of quantum gravity, a theory that unites Einstein's general relativity and quantum mechanics, to know for sure. There are some counter-arguments that the energy might spread out or that the saddle shape of the wormhole's throat might defocus the beam like a lens, preventing the explosion.
So there's a chance.
A slim one.
There is a slim chance. We cannot rule it out completely.
So, wrapping this all up, we started with this simple, straight railway track. We found out that nature doesn't naturally bend it for us with spinning universes or cosmic strings. We learned that speeding up doesn't work because of the infinite energy cost. But we can dig a tunnel.
We can build a wormhole.
We can prop it open with negative energy, which, amazingly, we know exists.
But if we try to step through, we risk getting vaporized by a vacuum energy feedback loop, or maybe getting stuck in a past where we have no free will and can't change anything anyway.
It's a very high-risk, high-reward venture.
It is, and that brings us to the final thought on this deep dive. The source material ends with a bit of a gamble. The betting man.
The author, and it's widely believed this was Hawking discussing his own work, says that even though the laws of physics might technically allow time travel, he's not willing to bet money on it being successful.
Why not? Hawking loved a good wager.
He said, I won't bet on it because my opponent might have the unfair advantage of knowing the future.
That is brilliant. You can't hustle a time traveler.
You really can't.
But I want to leave our listeners with something to chew on, something a bit more existential.
Go for it.
We talked about consistent histories, the idea that if time travel is possible, the past is fixed, you can't change it, you're already a part of it.
The block universe.
Yeah.
The idea that past, present, and future all exist simultaneously.
If that's true,
Yeah.
and if we are living in a universe where someone someday could eventually travel back to now, doesn't that imply that our future is already written?
It does. It implies that the future is just another place we haven't visited yet, but it exists just as solidly as the Roman Empire exists in the past, Our lives are just a path through that block.
So are we making choices right now? Or are we just playing back a recording? Do we have free will, or are we just watching the movie of our lives from a first-person perspective with the ending already spoiled?
If the loop exists, the script is already written.
That is a terrifying thought to have while you're just, stuck in traffic, moving forward at exactly 1 second per second.
It is.
But maybe, just maybe, that feedback loop saves us. Maybe the universe destroys all the time machines to protect our free will.
I think I'm rooting for the feedback loop. Thanks for listening to The Deep Dive.
Keep looking up.